Well, welcome back, everyone, and thanks for coming back. This is the continuation of the series of lectures I'm giving on experimental studies, using the randomized controlled trial as the example of the experimental study that we are discussing. So what I'd like to do now is talk about this notion of randomization. Why is it that the investigator is in the back of the room flipping coins to decide whether a person receives a new treatment or, say, a standard of care? What's the role of randomization? What implications does it cause in this study? Well, one reason we randomize is we want to take out of the treatment decision the role of the patient, the role of the patient's physician. What we don't want is the sicker people to receive the new treatment or the sicker people to receive the standard of care. That wouldn't be a very comparable study to compare. Sicker people receiving one treatment versus less sick people receiving another treatment. So if the investigator's flipping coins and the investigator is letting the coin decide whether a person receives a new treatment or not, you're even taking the investigator out of the picture. It's the coin that's deciding whether I get the new treatment or the standard of care. So what the randomization first does is remove the potential bias in the allocation of patients to receive a new treatment or a standard of care. Neither the investigator, nor the patient themselves, nor their physicians can decide that this person should receive the new treatment or this person should receive the standard of care. And as a result, randomization would tend to give you comparable groups. For example, let's suppose I'm having 10 very elderly people in my study. Elderly people might be at higher risk of developing my outcome. If these elderly people all receive the new treatment and none of them receive the standard of care, when I compare my two groups, those who received a new treatment versus those who received a standard of care, what I'm really doing is comparing new treated people who are old versus the standard of care people who are not old. I have a lack of comparability. So what does a coin do? A coin doesn't know your age when you flip it. Your age doesn't influence whether that coin is going to show heads or show tails. So when you randomly assign people via a coin flip to either receive a new treatment or a standard of care, there's an equal probability that an old individual will be assigned to the new treatment or to the standard of care. You would expect, if you had 10 older people, that 5 of them would receive the new standard of care, new treatment, and 5 of them would receive the standard of care. That's the implications of randomization. It tends to balance the two groups with respect to characteristics that could influence the development of the outcome. Now, we know from what Marcello's been talking about that if I flipped a coin 10 times, and the coin is, let's suppose it's a fair coin, any one flip has the same probability of showing a heads or a tails when the coin falls to the ground. Well, if you flip a coin 10 times, you would expect to get 5 heads and 5 tails. But would you be surprised to see 6 heads and 4 tails as a result of those 10 coin flips? Not at all. That's well within the realm of sampling variability. But if you flipped a coin 10,000 times, would you expect 6,000 of those to be heads and 4,000 of those to be tails? Well, not at all. That's a very unexpected event. So for large studies, when you randomize people to receive one treatment or another, you're almost guaranteed that the two groups you end up with will be very well balanced, very much comparable with respect to all risk factors that could influence the outcome. That's the glory of a randomized trial, especially a large randomized trial. The two groups you end up with are very similar to one another. They're equally old, equally percentage of males, equally containing people with high blood pressure. They should contain equal amounts of risk factors that increase your chances of developing an outcome. That's the glory of randomization in a randomized trial. Well, how do we do the randomization? Naively, I've been saying we have this physician, this investigator, flipping coins in the back of the room, the coins deciding whether you get a head or you get a tail. In practice, that's not how it's done. In practice, it's done the way Marcello showed you when he was talking about Stata. You can use a computer package to generate random numbers. And if if a randomly generated number is odd, that person might be assigned to a new treatment. If it was even, you might assign him to the standard of care treatment. So typically, it's not a coin flip. It's an equivalent to a coin flip done electronically on a computer using a software package. In older days, before we had computers, we would have in the back of statistics books tables of random numbers. Every number in this table was just as likely to be a 0, a 1, a 2, a 3, a 4, a 5, 6, 7, 8, or 9. There was no pattern to those numbers. So you could close your eyes and you could pick a point in that table. And starting at that point, you could read all the numbers to the right and say there were 10 numbers to the right. And that would determine how the next 10 people would be assigned in your study. And those sequence of those 10 numbers, since they are random, some would be odd, some would be even. That's the same essentially as flipping a coin. There's nothing wrong in conceptualizing a randomized trial as if someone's flipping a coin. The problem with flipping a coin is there's no electronic record kept. If I ran the program to generate random numbers, and Marcello was talking how to do that in Stata, talking about how to fix a seed. He pulled a dollar bill out of his pocket and chose that as the starting point for the sequence of random numbers. And that means if you went back tomorrow and generated a new set of random numbers with that same starting point, you'd get the same sequence. So one of the nice features of doing this using computers is you can have a record, a history of how the random numbers were generated. So if anyone challenges you about the integrity of your study, audits your study, wants to know how the assignment was done, wants to be convinced that it was random, you can show them the sequence of random numbers by using the actual seed that you used in that study. So this is typically how people get randomized in studies. What I'm describing is what is known as simple randomization. That's essentially what I mean by a coin flip. Now, simple randomization should give you balanced groups. But in a small study, let's suppose I only had 20 people in my study and 10 of them were very old, and I'm flipping coins, or I'm using these tables of random numbers, or I'm using this generated sequence of random numbers via Stata or some other computer program. I talked about before, if I have these 10 elderly people, coin flipping is expected to put 5 of them in the new treatment group and 5 of them in the standard of care group. But don't be surprised if it's 6 versus 4 or 7 versus 3. That's well within the realm of statistical chance. Is there a way to guarantee in small studies that equal numbers of old people will be assigned to one treatment and as assigned to the other treatment? So if you had 10 individuals, that only 5 of them would get the new treatment and only 5 of them would get the standard of care treatment. Well, there is a way to do that with randomization. It's an alternative to coin flips. It's an alternative to simple randomization. It's what we refer to as blocked randomization. What we, the investigators, decides to do is I'm going to enroll people into my study sequentially. But as I enroll people, I'm going to treat people who are being consecutively enrolled in a series called a block. So for example, when I'm talking about a block size of 4, I'm talking about the next 4 people who are going to be enrolled in my study. A block size of 6 means the next 6 people who are being enrolled in my study. What I want to do is come with a randomization scheme that constrains this block so that equal numbers of people are assigned to both the new treatment and to the standard of care. That guarantees balance within the blocks. So if I have 6 people in this block, 3 of them are going to get the new treatment, 3 of them are going to get standard of care. Not 4 versus 2, not 5 versus 1, but 3 versus 3. Well, how can I do that? Well, if I have a block size of 4 and I want to guarantee that 2 of these people in this block will get a new treatment, let's call that treatment A. And 2 of them are going to get the alternative, the standard of care, let's call that treatment B. There are 6 different ways you can sequentially assign people into my study. These 4 people under the condition that 2 of them get treatment A and 2 of them get treatment B. One of the possibilities is the following. First person gets A, next person gets A, third person gets B, fourth person gets B. When all 4 people enrolled, 2 of them got treatment A, 2 of them got treatment B. Another option is first gets A, next gets B, third gets A, fourth gets B. Or first 2 get B, next 2 get A. Or the first one gets B, the next 2 get A, and the last one gets B. My favorite, ABBA, the Swedish rock group from the 80s, I guess. First one gets A, next 2 get B, the last one gets A. And the only other alternative is first gets B, second gets A, third gets B, fourth gets A. There are 6 possible ways, only 6, that I can take 4 people, assign them sequentially into a study under the condition that at the end of the sequence of all 4 of them, 2 of them are given treatment A and 2 of them given treatment B. So how could I use that knowledge to randomize people into my study? I can write these 6 sequences. 1, 2, 3, 4, 5, and 6 on 6 separate pieces of paper. So the first one says AABB, the last one says BABA. Crumple them up, put them in a hat, close my eyes, and pick a piece of paper from the hat, and that's going to tell me how the next 4 people are going to be randomized. I can put that piece of paper back into the hat. I got 6 of them again, shuffle them up, pick another piece out. That's going to tell me how the next 4 people are going to be randomized. So before I start the study, I can come up with a randomization sequence using a block size of 4 that might tell me how all my 100 people in my study are going to be randomized. Each 4 of them are going to be randomized under a constraint that 2 of them gets A and 2 of them get B, randomly using one of these 6 assignment processes. I'm going to do that 25 times to tell me how all 100 people are going to be assigned. At the end of the day, after the 100th person is enrolled, it has to be that 50 of those people were assigned to A, 50 of them were assigned to B. If I had 101 people, or 102, or 103, if my study ended up with not a complete block being assigned to treatment A or B, the worst that can happen, if I had 103 people in my study, and I randomized using block randomization with a block size of 4, the worst that could happen is 52 people are getting treatment A and 51 people are getting treatment B. So block size guarantees that the total number of people receiving one treatment, say A, is almost going to be the same as the total receiving another treatment, B. Well, how is that going to help me when I do these randomized trials to assure I have balance with respect to some factor like age or sex or something like that? Well, before I talk about that, let me talk about the downside of block randomization. As I say, what I'm going to do is I'm going to reach into my hat and pick one of these pieces of paper out of the hat, and that's going to tell me how the next 4 people are being randomized. If I knew how the first person was randomized in that group, and knew how the second person was randomized, and knew how the third person was randomized, by definition, I'm going to know what the 4th person is going to receive. If the first person got B, treatment B, the next one got A, the next one got B, the last one, the next person in the door, is going to get treatment A. So that introduces a potential bias into my study if the investigator knows the size of the block and knows how the previous people in that block were assigned. They might know for certain that the next person in the study is going to get treatment A or treatment B. If the patients enrolling know the block size and know what the previous patients who were enrolled received for their treatments, they might know what they're going to receive, and if that's not the treatment they want, they might pull themselves out of my study. Or they might delay being into the study to a point where they hope, the treatment they want. Or they're physicians who are allowing me to enroll people, if they know the block size and they know how previous people were assigned, they might gerrymander the system somehow to get their patients the treatment they want. So block randomization has the potential of allowing people to predict whether they're going to receive one treatment or another in a way that they know in a very strong probability whether they're likely to get treatment A or treatment B, while simple randomization, the coin flip, means everybody has the same probability, 50%, of being assigned to treatment A or treatment B. So what we might do to minimize that potential bias is we could, first of all, not tell anybody the block size. So we don't know when the block begins and the block ends. We could also vary the block size The first 4 people are going to be enrolled with a block size of 4. The next 6 are going to be enrolled with a block size of 6. The next 2 with a block size of 2. That's a way to mask the treatment assignment, to help avoid that potential bias of patients themselves or their physicians or the investigator favoring a certain treatment for an individual by knowing the likely treatment assignment for the next person. Okay, so that's how blocked randomization works as opposed to simple randomization. Why is blocked randomization now going to help me in small randomized trials to achieve balance where simple randomization might not be? Again, remember the study I talked about. You have 10 elderly people. The coin flip, it's possible that 6 of them get one treatment, treatment A, and 4 of them get treatment B. We want to guarantee that 5 of them are given treatment A and 5 of those elderly people are given treatment B, and that's where blocking comes into play, along with something called stratification. So what we're going to do is we're going to, before we start enrolling people in the study, we're first going to put them into groups. We could stratify by age. As you enroll in my study, before I randomize you, I ask your age, and I put you in either the young group or the middle age group or the old group. And let's suppose 10 people are put into the old group. What I want is 5 of those old people in that old age group to be assigned to treatment A and 5 of them to assign to treatment B. So what I'll do is a separate blocked randomization in that group of 10 patients. If the block size is 2, I'm going to randomly assign people into treatment A or treatment B in block sizes of 2. I'll have 5 of those random assignments. Guarantee at the end of the day, 5 people get treatment A and 5 people get treatment B. So what I'm going to do is within Strata, I'm going to assign people to one treatment or another, not using simple randomization, but using blocked randomization. That's going to guarantee balance with that factor I stratified by. Okay, so what should I stratify by? I should stratify by factors that I think could have a major influence on whether a person develops an outcome or not. Potential confounding factors. We'll talk more about confounding in future weeks. Things like study site. If I'm enrolling people from different hospitals around the country, or stage of disease, I want to make sure that equal numbers of very sick people, high stage of disease, are assigned to treatment A or treatment B. So to show you how this works, let's look at the following hypothetical example. Let's suppose we have 3 sites we're doing our study. Think of these as 3 different hospitals around the country. Site A, Site B, and Site C for hospitals A, B, and C. Let's suppose we're comparing a new treatment versus a standard of care for a condition that's very uncommon. So the reason I'm doing a multi-center study at multiple sites is I don't get enough patients at any one hospital to answer the question whether treatment A is better than treatment B. I have to take patients from different hospitals from different parts of the country. And maybe the patients who go to one hospital, say Hospital A, are the sickest people. It's a major referral hospital. People come there from all around the world. So Hospital A is really your sickest people, and hospitals B and C might be your less sick people. I want to make sure that equally sick people are assigned to groups A and to group B. So what I'm going to do is block randomization stratifying by hospitals. So here's my Hospital A. It has 12 people that's going to be enrolled in my study. I'm going to use a block size of 4. I'm going to pick one of those 6 sequences of numbers or letters. And let's suppose the first one I pick is A, B, B, A. That tells me how the first 4 people from Hospital A are going to be assigned. The next 4 are going to be assigned in the sequence of A, B, A, B, the last 4 in B, A, B, A. For hospital number 2, Hospital B, let's suppose I have 8 patients enrolled from that hospital. Again, I'm going to use block randomization separately within that hospital. I'm going to pick one of those 6 sequences at random, and let's suppose it's AABB. That's how the first 4 people from Hospital B are assigned. The next 4 are assigned with ABAB. And then finally, if Hospital C only has 4 people, let's suppose they're assigned by BBAA. That's what happens separately within each hospital. Now, at the end of the day, if I compare everybody into one analysis, I end up having 12 plus 8, 20 plus 24 people in my study. Let's see how well the blocked randomization worked. If you count the number of people who got A, it's going to be 12 people. If you count the number of people who got B, it's going to be 12 people. So one thing that's coming as a as an implication, as a result of block randomization, is equal numbers of people in my entire study are given treatment A versus treatment B. That might not happen with simple randomization. Flip a coin 24 times, once for each person. You expect to get 12 heads and 12 tails, but you're not going to be surprised to get 13 heads or 14 heads. Imbalance might happen in terms of the total numbers of people. Blocked randomization occurs that it's either going to be perfectly balanced or if at worst, only one or two more people it might be in treatment A or treatment B because at any particular hospital, if you don't fill a complete block, the worst that can happen is if you only enroll two people, is that both of them are going to get treatment A or both of them are going to get treatment B. The total number of people within the hospital receiving A or B is at worst off by 2 people if you're using a block size of 4. But more importantly, let's look at the distribution of the 12 people who received treatment A in terms of which hospital they came from. 6 of those came from hospital A. 4 of them came from hospital B. 2 of them came from hospital C. Same exact numbers for those who received treatment B. Because I blocked and stratified by hospital site, I'm guaranteeing that the factor I stratified by hospital site is almost going to be perfectly balanced in this small randomized trial. So the best way to guarantee balance, to guarantee comparability in small randomized trials is to, whatever factor you're mostly concerned about as potentially being not balanced, is stratified by that factor, like hospital site. Do separate blocked randomizations within each of those strata. And that'll guarantee at the end of the day that that factor you stratified by will be nearly perfectly balanced in the 2 groups you end up comparing in your analysis. Well, that's all I wanted to say about randomization. When we come back, I want to talk about things that happen after randomization in experimental studies. I want to talk about blinding, and the role of blinding. So I'll see you next time.